Hey everyone, and welcome to this explainer. Today we're diving into one of the absolute heaviest, most computational bottlenecks in materials engineering. I'm talking about predicting exactly how complex woven composites behave under stress, and doing it without getting stuck waiting weeks for simulations to finish. We're going to break down a really fascinating paper by Gane, Fagerstrom, and Merkeloff. It's called A Multiscale Deep Learning Model for Elastic Properties of Woven Composites. We're going to walk through their methodology step by step, taking a close look at the data and the framework right from the source. So let's jump right in.
Okay, so here's the core problem we're dealing with. If you're designing a woven fabric composite, you need a model that can handle all sorts of different fiber types and matrix systems, right? Because the ultimate goal is to tailor these materials to find that absolute perfect sweet spot, the best trade-off between structural properties and cost. But to pull that off, you need a model that can accurately predict the macroscopic elastic behavior based entirely on the properties of the raw ingredients at the microscale. Now, the traditional gold standard for this is multiscale finite element analysis. And don't get me wrong, it is incredibly high fidelity, but there's a huge catch. It is computationally exhausting. If you want to explore a really high-dimensional design space to find the best possible material combination, you're literally looking at weeks of processing time. Who has time for that?
Before we get to the really cool speed-up part, we kind of have to understand the baseline method first, computational homogenization. In a standard simulation, you obviously can't model every single microscopic fiber in a massive composite part. It's just impossible. So instead, engineers define what's called a representative volume element, or RVE. Think of it as a tiny, manageable little block that statistically represents the whole chunk of material. By applying periodic boundary conditions and putting this RVE under unit strains, you can calculate the volume averaged microscopic stress. And this gives you the homogenized stiffness tensor, basically the relationship between the macroscopic stress and macroscopic strain. It's super accurate for sure, but doing this across multiple scales, going from one tiny microscopic fiber all the way up to the massive woven structure, that right there is exactly what causes that massive computational traffic jam we just talked about. Well, that brings us right to the researchers' overarching, data-driven solution. Instead of just grinding through those heavy calculations during the design phase, they introduce a framework that totally changes the game. It transitions across two distinct scales, a micro-ANN that feeds directly into a meso-ANN. Essentially, they're using machine learning as a surrogate model. Why? To completely bypass that crazy expensive lower-scale physical material modeling. By training these artificial neural networks to actually understand the physics of the material, they can instantly spit out the stiffness tensors that would normally take a supercomputer a very, very long time to crunch.
Let's actually break down what these two neural networks are doing. First up is the micro-ANN. Its entire job is to look at the unidirectional composite, the individual fibers just sitting inside the resin matrix, and predict the homogenized properties of a single yarn. It takes inputs like the matrix stiffness, the fiber stiffness, and the fiber volume fraction. Then it grabs those predicted yarn properties and literally hands them off to the second network, the meso-ANN. The meso-ANN takes that data and estimates the overall elastic behavior of the whole plain weave fabric. So the absolutely crucial takeaway here is that once these two surrogate models are fully trained, they team up to let you skip the finite element modeling entirely when you're testing out new material combinations. It's a total shortcut.
You can really sense the scale of the complexity when you look at these two side by side. On the microscale, you've got the spatial discretization of a unidirectional RVE, basically these red fibers randomly scattered inside a blue matrix. To get the accuracy they needed here, the researchers used elements that were 6 times smaller than the actual fiber diameter. Pretty tiny. But then, stepping up to the mesoscale, you see this incredibly complex geometry of interlocking yarns in a plane weave RVE, mapped out with a von Mises equivalent strain distribution. To capture that level of complexity, they had to use a mesh with 100 by 100 elements in plane, plus 50 elements just along the thickness. You can quickly see why trying to combine these two highly detailed scales into one continuous analysis is just so incredibly heavy on a computer.
Now, as we know, to train an artificial neural network, you absolutely need data. And not just any data, high-fidelity data. To get this, the researchers had to set up an automated, massive batch mode process. In step 1, they used a software called Digimat FE to automatically generate 3D unidirectional RVE geometries. Then, in step 2, they ran a custom Python script to do the finite element simulations on these RVEs, applying those periodic boundary conditions to mimic real-world physical constraints. Finally, in step 3, the script automatically extracts the homogenized stiffness properties. And here's the kicker. Every single time this automated process runs, it takes about 10 minutes of CPU time just to create one perfectly accurate data point for the neural network to learn from.
Because each of those data points takes 10 whole minutes to generate, standard sampling techniques just weren't going to cut it. You can't exactly run millions of them. They had to be really, really smart about how they sampled their 5-dimensional design space, which includes variables like fiber stiffness, matrix stiffness, and volume fraction. If you just use random or stratified sampling, you often end up with these clumpy clusters and massive empty gaps, meaning you'd need huge data sets to ensure the network actually learns the whole picture. So instead, the researchers used something called solvable sequence sampling. It's a quasi-random method designed to spread points out as uniformly as humanly possible over a multidimensional space, actively dodging those clusters and gaps. It's ridiculously efficient, even when you only have a small amount of data to work with.
And in practice, this solvable sequence sampling works like an absolute charm. When you look at how it maps pairs of different input parameters, say the matrix Poisson's ratio versus fiber volume fraction, or fiber stiffness versus matrix stiffness, the data points are laid out perfectly uniformly. There are no dense clumps and no empty blind spots where the neural network would be left guessing. Because this technique is so efficient, the researchers ran a convergence study and figured out they only needed 400 data points to properly train their models. Just 400. That saved an unbelievable amount of time during the data generation phase.
All right, so with the data locked in, it was time to actually train the ANNs. For the architecture, they went with feed-forward multi-layer perceptrons. In these types of networks, the neurons in one layer connect in just a single direction to all the neurons in the very next layer. During training, the network makes a guess, a prediction, and then compares it to the actual true target value from that finite element data we talked about. It calculates the difference, which is called the mean square error cost function. Then, it uses a really cool process called backpropagation. Basically, it works backward through the network, constantly tweaking and updating the connection weights and thresholds to shrink that error down. It's kind of like tuning a guitar string over and over until the pitch matches the real high-fidelity physics perfectly.
Now, deep inside those neural networks, the local fields of the neurons have to be processed by an activation function. This basically mimics how a real biological neuron in your brain fires when it gets a signal. For this, the researchers specifically chose the rectified linear unit, or ReLU for short. It's pretty straightforward. It just outputs the input directly if it's a positive number and spits out a 0 if it's not. But why does that even matter? Well, ReLU is incredibly good at solving a massive headache in machine learning called the overfitting problem. Overfitting is what happens when a network essentially just memorizes the training data like a flashcard, but fails to actually learn the underlying physics. By using ReLU, they made sure the network actually generalized the physics, meaning it can make highly accurate predictions on completely new, unseen material combinations.
Okay, I want you to hear this number because it really puts the whole thing into perspective. 2,930. That is the number of seconds, almost 50 straight minutes, it took a standard computer to run just a single, traditional mesoscale simulation using finite element modeling. The meso-AIN, it completely bypasses that step, spitting out those elastic properties based on the inputs almost instantly. But, speed means absolutely nothing if the accuracy isn't there, right? To prove this actually worked, the researchers had to rigorously validate the multiscale deep learning model for these woven composites, and the results are stunning. If you look specifically at the validation highlighted in figures 8 and 11 of their study, it confirms that the ANN's instant predictions lined up almost flawlessly with the expensive, time-consuming finite element calculations. They seriously achieved incredible speed without sacrificing an ounce of fidelity.
So, what is the big takeaway from all of this? Ultimately, it's a massive, validated acceleration in simulation-driven design. The researchers proved beyond a doubt that neural networks can reliably replace that grueling, time-consuming micromechanical finite element analysis of unidirectional composites. By chaining a micro-NN to a meso-NN, they built a truly generalized approach. Now, an engineer can just plug in a huge range of dry resin properties, fiber properties, and yarn volume fractions, and boom, instantly receive the estimated elastic engineering coefficients for that specific weave architecture. It is the absolute perfect balance, extreme computational efficiency paired with the rigorous accuracy that high-level materials engineering demands.
Honestly, this incredible intersection of deep learning and complex physical modeling is really just scratching the surface of what's possible out there. If you found this framework even half as fascinating as I did, and you want to dive deeper into the ongoing work from Dr. Merkelflaff's group on the mechanics and physics of materials, you absolutely should go check out their site at materialslab.org. But before we wrap up, I want to leave you with a thought to chew on. If multiscale physics can be this accurately learned and instantly predicted by an artificial neural network today, what other impossible computational bottlenecks in engineering design are about to vanish entirely tomorrow?
Thanks so much for joining me on this explainer, and I'll catch you next time.